Okay, so we were looking at the ionization probability last time, and what we saw was that if one works in the parabolic cylinder coordinate system, then one can write down equations in c variable as well as in eta variable, and we find that if we turn on the electric field in z direction, uh, then the problem in C variable is stable. There is no way that the bound state could ever decay. On the other hand, in the eta variable, there is a tunneling probability. Okay, uh, so okay, so the thing is that even if there is a tunneling probability, we uh, what we find basically is that we need to uh, look at the potential, and the potential was something we saw that it goes up and kind of turns around and goes down again. And for any bound state, there exists some barrier that it has to overcome for the electron to get out of the bound state and become free. Okay, which is what we would call ionization. Okay. So what we expect, therefore, in this particular setup is that for small values of eta, where the bound state problem is well defined, we would expect the wave function to be the wave function of the bound state problem, which will give a kind of uh, reasonably good description of the electron in small eta region. And for large eta region, where the electric field would eventually dominate, even if electric field is weak, if you take eta sufficiently large, the potential would turn around, and you would want your wave function to be an oscillatory wave function. Okay, and the region in between, which is what is called the potential barrier, is a region in which the solution would have a decaying form, and we need to match that wave function in the classically disallowed region with the wave functions on the classically allowed regions. One classically allowed region is small eta region, which is where the bound state wave functions are there. And the other classically allowed region is large eta region, where the electron is supposed to be free particle. Now, of course, if you encounter a situation like this, one a nice approach to the problem of this kind is to use Wkb method. And so in the Wkb method, what we will do is we'll look at this potential, and we will call this classically disallowed region as region 1, classically allowed region as region 2. And hello, is my voice breaking? Can you hear me properly? Hello?
Yeah, I mean it's breaking a bit, but I think it's okay.
It's okay. Okay, so maybe I'll try to speak a little slower. Hopefully that would help. Mm. Okay, so in the region on the left, small eta is a place where we are going to assume that our wave functions are going to be bound state wave functions. We will have to kind of give a WKB ansatz for the wave functions in region 1 and region 2. Okay, so here is the thing. I hope you can read my handwriting. So we have the wave function which we will call g of eta. Remember, we have already done separation of variables, so we don't have to worry about phi and phi coordinates because they are not playing any role here. So our wave function is a function of eta only, and g of eta is some constant b plus times q eta to the minus half times exponential of integral of q eta prime d eta prime, where eta prime is integrated from eta naught to eta. Okay, plus b minus times q eta to the minus half times exponential of minus the same integral. Okay, that is the form. B plus and b minus are to be determined. These are just normalizations of these wave functions, and q to the minus half times exponential integral of q is the typical WKB answers um, for the leading the term in the exponential is the leading answers, and q to the minus half is the first correction to the leading answer in the WKB. Okay, uh, it is. I mean, if you get time to look at differential equation stories at some other point again, then you will see that the there exists some method called method of dominant balance, which would also give a solution of this kind. Uh, in the neighborhood of irregular singularity, really. Okay, so one would be able to kind of get a better picture of why one gets a solution of this kind by uh, just solving a differential equation. Okay. Mm. Fine. But coming back to what we were doing was this Q is basically just square root of 2m times V eta minus E. Uh, and that is the quantity sitting around there. Okay. Now, uh, it is written as V eta minus E because we are in the classically disallowed region, in which case V eta minus E is actually positive. Okay. So therefore, there is no uh, factor of plus or minus I sitting around here because this quantity inside the square root is positive. And as a result, the wave function is that we have written down is exponentially growing or exponentially decaying solution. Okay. And we have to match this wave function at the boundary, at the left boundary with the bound state wave functions in the classically allowed region for small eta. Okay. Now we know how the wave function is looking in the classically allowed region in and its behavior and behavior of that bound state wave function for larger values of eta. Namely, it should fall off as e to the minus eta. Okay. In fact, we have solved this equation, and it is actually the answer is e to the minus beta times eta by 2. Okay, and beta was some quantities quite similar to this one. Okay. So clearly, given the fact that the wave function from the bound state problem is exponentially decaying, the only way you could match that wave function with g of eta is if b minus is kept to be non-zero and b plus is kept 0. Because if b plus is non-zero, then you are trying to match an exponentially decaying solution with an exponentially growing solution. Okay, so simple exponentially decaying wave function matching across this classically allowed region, boundary of the classically allowed region tells us that b plus should be set to 0. Okay, fine. Now we have to, of course, normalize g of eta, and normalize means just determine what b minus is. Okay, and that can be done by just comparing the normalized wave function in the bound state sector with the wave function g of eta when you match the wave function across the classical boundary. Okay, so therefore a normalized wave function of the bound state problem would help us determine what b minus is. Okay, we will not do it explicitly, but we know what those normalizations are. The normalized wave functions in the um, parabolic cylinder coordinate system are available. All we have to do is to kind of look it up somewhere. Probably some books like Schiff's book on quantum mechanics may even have solved the problem explicitly. If it is not solved, we can just normalize it. In fact, this was one of the exercises as to determine the integration measure in the parabolic cylinder coordinates and use that integration measure to normalize the wave function. So once you do that, you would be able to determine what b minus is. Okay, by just matching wave functions across this boundary.
So,
Yes.
are we considering an approximation where V2 is small? I mean, the Z potential is small.
So this potential is small, no? Why?
The thing that actually like reduces the barrier. I mean, we are earlier saying something like if the potential is small, it
Hmm.
will only happen at large eta.
That is right. Yeah.
This tunneling effect.
Yes.
Yeah, so
Yeah.
I mean,
So
it
we are
seems to
looking
me
at the
like we have set, uh, we are comparing at boundaries, at the left boundary,
yeah.
we are trying to compare the solution with the bound state solution.
Yes.
But we are, but why should we compare it with the like e to the power minus beta eta by 2? That is valid only at like far away.
That is right. Yeah. But uh, the full wave function has an exponential sitting around, no? Right?
Yeah,
So therefore, there is an exponential piece in the wave function that needs to be matched at the boundary, right? Very far away, it is the exponential which will dominate, but the exponential is there everywhere, right? Is that okay?
okay.
So what we are trying
I
to
mean,
say is that,
usually
yeah,
what we do is like match the coefficients. We get one equation in b plus and b minus, then we differentiate and match, and then we'll get
yeah,
another equation in b plus and b minus.
yes, yes, that is true. But that is not the way you do WKB. That is the way where you do kind of barrier penetration computation by matching the wave function and their derivatives.
Yeah,
Yeah. So, but in WKB, what you do is actually you do a linear approximation across the classical boundary and try to match the wave function, right? Okay.
okay.
You say that you approximate the potential to be kind of linear around the classical turning point, and then you kind of uh, take small region, write down a linear problem, and match the wave functions on both sides of that linear region. Okay. So what we are
We
doing is
didn't
that
do it yet, right?
we are no. So what we are doing is we are bypassing that, and we are just saying that like no, we know how the solution is going to behave inside the barrier. Okay. And uh, okay, I mean, you don't even have to match this way. I can give you another physical reason as to why B plus should be zero, and that is that if you are looking at a problem where the particle is kind of tunneling through a classically disallowed region, then there is no way that the wave function is going to be exponentially growing. Okay, because the probability of classically disallowed of the wave function, sorry, probability of particles being found in classically disallowed region is exponentially damped. This is like an evanescent wave, right? And therefore, you would expect the solution to be exponentially dying and not exponentially growing. Okay. So even without trying to match that with on the left hand side, you could have just said that B plus should be zero simply
Yeah,
because
yeah,
you are
I
saying so.
understand the physical argument. I'm just
Yeah.
saying that in order to actually state that V plus is zero, we should compare at both boundaries and say that at the
Huh.
right boundary, the wave function will actually vanish, like
No.
exponentially
So no.
decreasing.
So I am still looking at region one on the left boundary. I have not said anything about region two yet. So when I'll come to region two, I'll match the wave functions here also.
Yeah.
Is that okay? So right now I'm doing only this part of the story. Once I write down these wave functions, then I'll do this classical turning point also. Okay.
Okay.
So as I said in the last class that we will just set up the problem. We'll not exactly solve the whole problem because it depends on various parameters that we need to look at. But how we will approach the problem is what we will look at today. Okay. And not exactly kind of you know plug in exact potential and try to integrate and get the solution. Okay. So, so right now we are only looking at one part of it, which is only uh, half the story. We'll have to look at this part also, match those, and then get the answer. Okay, is that fine? Okay, so let's get to region two now. Okay, in the region two, uh, as we know that it's a classically allowed region and the particle is free to escape all the way to infinity. So therefore, you expect the solution to be uh, oscillatory. Okay, and therefore our wave function g of eta in the region 2 would be some other normalization constant a plus times p of eta to the minus half exponential I times some eta naught tilde, some other turning point. Okay, so like this is eta naught, whereas this is eta naught tilde. From eta naught tilde to eta, integral of p of eta prime d eta prime. Okay, and the other solution is e to the minus I. Now, in this particular case, of course, you cannot eliminate any one of the two because both of them are oscillatory solutions. This solution corresponds to a right moving wave, whereas this corresponds to left moving wave. Okay, and P, yeah, so I think there is a small typo here. It should have been E by 4 really. Okay, yeah, but E by 4 is the correct ground state wave function with our normalization. If you look up the notes, you will find that it should have been E by 4. Okay, so P in this particular case is such that the potential V2 is less than E by 4, and therefore E by 4 minus V2 times 2m is a quantity which is positive definite, and therefore sitting inside the square root does not give you any factor. Okay, so plus minus I have already been pulled out in switching V2 positions of V2 and E. Okay, fine. Now A plus A minus have to be determined by matching the solution at the turning point eta naught tilde. Okay, that will be done by comparing that with B minus of this wave function that is defined in region 1. Okay, so that is the condition where, of course, you would require matching the wave function as well as its derivative to be able to kind of determine these two in terms of the third variable. Okay, fine. Now, after we have done determination of A plus and A minus, then what we want to actually determine is the right moving current, because right moving current in this particular case is the one which tells you the ionization probability, because the current which is moving in the right direction tells you that the electron is actually getting out of this barrier and escaping to infinity. Okay, so what we want to do is to compute the right moving current, which would give us the rate of decay. Okay, now the point is that, like, this entire method would work provided we have this decay rate being very small. Why? Because if the decay rate is large, then a lot of things would go wrong. First thing that would go wrong is that if the decay rate is very large, then most likely that the potential is kind of going just a little above the energy and turning around. There's only a small gap, or rather small barrier. Okay, if the barrier is very small, then it is kind of the approximation that we have used, saying that like we are going to match this Wkb wave function on the left with the bound state wave function is not correct. Simply because if the barrier was very small, then the bound state wave function itself may be an approximate wave function, may not in fact be a reasonably accurate description in the neighborhood of the turning point. And then you really have to do a little more rigorous Wkb approximation by drawing some small region around the classical turning point, make a linear approximation, write down Airy function problem, and take Airy wave function and match the oscillatory part of the Airy wave function on the bound state side and exponentially decaying part of the Airy wave function on the barrier side. Okay, and that one we will have to do both on the left turning point as well as on the right turning point if the decay rate is large. Okay, so therefore whatever we are doing right now would be more sensible if the decay rate was small. Okay, that would allow us to kind of, I mean, it's not completely accurate, but still to a reasonable accuracy, it would allow us to use the bound state wave functions on the left hand side. Okay, fine. So what we will find is that this problem, this problem would have a decay rate, we should go as some exponential of minus some constant by the strength of the electric field. Okay, we are not actually going to do this calculation because that would probably take a couple of lectures for us to do. Okay, but the point is that if the electric field is very large, okay, then you would find that uh, uh, that the uh, e to the minus c by e is closer to 1. Okay. On the other hand, if the electric field is very small, then it is e to the minus very large number and the decay rate is very small. Okay, so you would have expected a tunneling event to go inversely proportional to the strength of the electric field. Okay, so that is the kind of result one would eventually derive from this. Okay, fine. So what we have done so far actually is we have studied various things about single electron atom, where we have looked at various we have looked at various corrections like relativistic corrections or corrections due to the nuclear spin and so on. But what we have done, and also things like ionization of the atom, what we will do now is to study transition between the energy levels. Okay, that is something we have not looked at yet. Okay, now to study transitions which are affected by an electromagnetic wave, we will start with study of electromagnetic wave first and set it up in a proper fashion so that we can study the behavior of single electron atom in the background of electromagnetic wave. Okay, fine. So electric field and magnetic fields are written like this: E is equal to the gradient of phi minus del A by del T, and B is curl of the vector potential, and A0 is just minus of phi. Okay, the Maxwell's equation in free space would be del dot E is equal to 0 and del cross B is equal to del E by del T. And we will work in the Coulomb gauge. This is the gauge that we have been using right from the beginning. So if you use a Coulomb gauge, then del dot E equals 0 would tell you that this term would just drop out and Laplacian acting on phi would be equal to 0. Okay. Now, since we are in the free space, that means there are no charged particles in the space. There is no Coulomb potential, and as a result, this Laplacian acting on phi is equal to 0 is actually solved by phi itself being 0. Okay, and so as a result, we could kind of reduce E to be just minus del A by del T. Okay. The second thing is, of course, del cross B equals del E by del T equation. You can substitute B to be curl of A, and that gives you an equation which is like this: that curl of A is equal to del E by del T. This equation can be simplified by using the explicit expression for the curl. So you can write that as epsilon ijk del j times curl of ak, but curl of ak itself can be written as epsilon klm del L of am. And now you notice that you have epsilon ijk, epsilon klm with k index repeated. So that tells you that this would give you delta IL, delta JM minus delta IM, delta JL. Okay, so we will use that to write down this expression, and then use and this del J would just act on del L of AM. Okay, right hand side of is, because E is equal to minus del A by del T, just gives you second derivative of AI. Okay, this index I just is used to match with the free index on the left hand side. Okay, good. So what we need to do is to basically get these fellows to work with uh, so you suppose you look at delta IL delta JM case, then you find that this equation would become del M del I of AM, but that term would be zero because we are working in a del dot A equals zero gauge. Okay, so only term that contributes is the second one, where um, M gets replaced by I and J and L are equal, so that is like Laplacian acting on AI. So the equation that you actually get is minus Laplacian acting on AI is equal to minus del squared AI by del T squared. Okay, which is of course the well-known wave equation or the Klein-Gordon equation satisfied by AI. Okay. Now, of course, this is the equation that you would see in A0 equals 0 gauge. Sorry, the del dot A equal to 0 gauge. Okay, the Coulomb gauge. Okay. Mm, so, mm, so what we will do is we'll try to solve this equation to find out what form of AI that we would have, and we would want to use that as the background. Okay. Of course, this is like a wave equation, and therefore we will have plane wave-like solutions. So the general solution for fixed value of the spatial momentum k would be something like a vector of x is equal to a omega times epsilon hat times cos of k dot r minus omega t plus some delta omega. Okay, where omega is just the modulus of the wave vector k. Okay, epsilon hat is the polarization vector. Okay, so that is what takes care of this vector thing. This basically a unit vector. That's why the hat. Phi of r equals 0 is just a statement that there is no Coulomb potential. Okay, and del dot A equals 0 condition tells us that when you take the derivative of this, you would get a k outside when you take the derivative. So you have to basically set k dot epsilon hat is equal to 0. This statement basically just tells you that in the three-dimensional space, if k is a momentum vector, then epsilon, which is the polarization vector, lives in a plane perpendicular to the momentum vector. Because if the epsilon is perpendicular to k, then its dot product would vanish. Okay. So in three space dimension, therefore, you have only two linearly independent vectors that you could write down, and therefore that is the reason why we say that the electromagnetic wave has two polarizations. Okay, fine. A omega is just the amplitude of this wave function. Okay, so that just tells you what is the intensity of the, I mean, it is related square, mod square of that is actually the intensity of the electromagnetic radiation. Okay, fine. So this statement about k dot epsilon equals 0 tells us that you could choose epsilon any which way you want, provided it is living in a plane orthogonal to the direction determined by k. So there are various ways of choosing it. You can have a plane polarized solution in which epsilon and epsilon hat 1 and epsilon hat 2 are two vectors which are orthogonal to each other, and both of them are orthogonal to k. The other possibility is to kind of have right circularly polarized versus left circularly polarized thing, which is also another possibility, which is some linear combination of the epsilon 1 hat and epsilon 2 hat that I just talked about. Okay, now of course what we are interested in is not some kind of a monochromatic kind of solution. This solution would correspond to a monochromatic wave because it has a fixed k and a fixed omega. But what we are looking at is some kind of a electromagnetic radiation with some spread in momentum and energy. So what we would write down is something like A as a function of R and T as integral d omega A omega times epsilon 1 hat times cos k dot r minus omega t times delta omega 1 plus epsilon 2 hat cos k dot r minus omega t plus delta omega 2. Okay, and we will of course be integrating over all kinds of omega. Okay, now since this equation is linear, if you take linear combinations of the solutions, that is also a solution. So therefore we don't have to worry about this superposition, whether that is a solution or not. Okay, that is in some sense guaranteed. Okay, now what you could do is you can generalize this solution to kind of integrating over all spatial momenta also, and you can write down A as integral d cube k ak times epsilon 1 hat as a function of k and so on. Okay, so you can check that this also can be done, and it would still guarantee that it's a solution to this equation. Okay, fine. So once you kind of get a solution of this kind, then you can determine the electric field, because electric field is just minus del A by del T, and that would just mean that you are taking derivative of this cost function, and derivative of this cost function with respect to T, which will kind of pop the omega out, and you get an expression which is minus integral of this quantity with the omega sitting outside, and this function becomes sine function. Okay, fine. Similarly, you could take a curl of this expression, and by doing that, curl would take a k out, but instead of giving you a term which is k dot epsilon, you get a term which is k cross epsilon, because it is a cross product. Okay, I'm writing that as k hat cross epsilon hat and pulling out omega, because omega is just the magnitude of the vector k. So magnitude of k times k hat is the same as k vector. Fine. So what we do is we can compute energy of this electromagnetic radiation, and energy is given by integral of E vector squared plus B vector squared. Okay, so you can check this by starting with the relativistic formulation of the Lagrangian density to be f mu nu, and try to determine the corresponding Hamiltonian, and you will find that it will turn out to be E squared plus B squared. Okay, so this expression is 1 over 8 pi times integral d cube r times E squared plus B squared. That is the total energy, and all we have to do is to take these expressions and plug them in. Okay, so when you plug these expressions in, you get terms which are quadratic in A omega, simply because these are quadratic objects. Okay, so you get A omega prime times omega prime times sine functions multiplying each other. Okay, factor of 2 comes simply because of E squared and B squared both contribute expressions which are quite similar. Okay, yeah, I mean, it's written out here also. Okay, fine. So we need to kind of determine this, and this can be determined only if we know what are the profile functions for this amplitude of the electromagnetic radiation. Okay, fine. Now let's consider a situation of incoherent radiation. Okay, so coherent radiation is more like a monochromatic wave with fixed phases. Okay, and incoherent wave function, incoherent radiation is would be something like it can have various different frequencies, but even if it was monochromatic, it would have the different waves, you would have different phases. Okay, so those phases don't have to add coherently. They may kind of add incoherently. So what you need to do is that you don't take sum of the wave function and take mod square, but you take mod square of the wave function and then add. Okay, so coherent sum versus incoherent sum corresponds to the following thing, that if you have two, let's take two wave functions just to get an idea. A coherent sum would be psi1 plus psi2 mod square. Incoherent sum would be psi1 mod squared plus psi2 mod squared. And the difference between the two is that there is no cross term, there is no overlap between the two wave functions. Okay, so what we are going to look at is the incoherent radiation, in which the phases are random and therefore the cross terms would vanish. Okay, fine. So yeah, so this is what I'm trying to say here, that at any given space point, various photons superimpose to give an effective electromagnetic field. And even if the waves are monochromatic, their phases are random. Okay, and okay, so because the phases are random, even if you are sitting at one particular spatial point, you will find that the phases are actually time dependent. Okay, because at different instance you have different superpositions of these wave functions, different superpositions of of the photon. Okay, uh, and as a result, you cannot expect the phases of uh, of the photons which are kind of arriving at a particular spatial point to superimpose in a kind of coherent fashion. Okay. Now, notice one thing, that I'm talking about this delta omega piece, which is a random phase, and uh, this random phase would be kind of effectively time dependent. But there is just an explicit time dependent phase out here, and what one is talking about is that the rate at which this quantity would change is much smaller than the rate at which the omega t factor would change. Okay, so it is not like this fellow is going to overwhelm the omega t oscillations of the wave. Okay, this is the kind of slowly kind of changing wave, but at any given point, if you have an incoherent sum of large number of photons arriving at that point, then effective value of the phase may be time dependent. Okay, so okay, so what is the offshoot of this kind of stuff? Or before that, like, why is it that we are considering something like this? Now, the reason why we are considering something like this is because when you shine light on atoms which are generated by some, you know, some spark light or stuff like that, that the light emitted by the spark lights uh, uh, are not coherent. They produce all kinds of waves, all kinds of frequencies, and those frequencies are not in coherence with each other. The phases are not coherent as compared to keeping the atom in exposing the atom to, say, a laser light. The laser light is typically monochromatic, and they have the same phase. Okay, so therefore, if you expose atoms to laser light, then you should not be doing something like incoherent study of incoherent radiation, but you should be studying coherent radiation. But most of the other cases, the light is supposed to be incoherent. Their phases are randomly arranged, and therefore most of the problems that we look at when atom is exposed to electromagnetic wave, it makes sense to use incoherent approximation. Okay. Now, uh, if you have an incoherent superposition, then what you should be looking at is the averaged electromagnetic field configuration and not the specific electromagnetic field configuration, which depends on a specific form of electric or magnetic field. Okay. Okay. You need to kind of really average over all these delta omegas. Okay. Fine. Now, remember that we have expanded the fields in the real basis. We are using sine and cos like functions and not the e to the I k dot x kind of function. Okay. The omegas therefore would always be positive semi-definite in that case, and averaging over phases would tell us that we should set e to the I delta omega times e to the I delta omega prime. Okay. This averaging, we will set that equal to 0 because, you know, the averaging process tells that this answer should be equal to delta function of delta omega minus omega plus omega prime. But since omega is positive, delta omega plus omega prime will never be 0. Okay, so therefore this expression would vanish. On the other hand, if you have e to the I delta omega times e to the minus I delta omega prime, then this will give you a delta omega minus omega prime with some normalization. And this, of course, has a chance of clicking when omega is equal to omega prime and both omega and omega prime being positive. Okay. Fine. Now, remember that these are just phases. Okay, so therefore they are dimension independent quantities, whereas delta omega has dimension of inverse energy. How do we know that? That we know because of the property of the delta function, and that is the following: that if you write down delta A of x, then delta A of x is 1 over mod A times delta x. Okay, that means it tells you that whatever is the argument of delta function, okay, its dimension is opposite of the dimension of the argument. Okay, because delta A of x is 1 over A delta x. Okay, so therefore, if you have written down delta of omega, then delta of omega has dimension of 1 over the dimension of omega. Dimension of omega is of course energy, so therefore delta of omega has a dimension of 1 over energy. Okay, left hand side is just a number because they are just phases, and therefore this constant that we are writing down here has the dimension of energy. So that energy times 1 over energy would make the right hand side dimensionless. Okay, is that fine? Are there any questions? Okay, maybe not. Okay, so what we could do is that we can use this fact that even if the phases were random, okay, average description would require that averaging of the phases would give us a delta function. Okay, so you can use that to simplify the expression for energy. Okay, so what you would get is, so let's go back to this expression. So you have this quantity. We can write down these sine functions in terms of exponential functions. Okay, and those exponential functions would involve e to the I delta omega, e to the minus I delta omega, and similarly delta omega prime. Okay, then we will say that the average energy would require averaging over various quantities, including the phases. Okay, those phases would give us a delta function, okay, of this kind. Okay, and you would get only 2 delta functions, although there are 4 such terms. Okay, notice you have a term which is e to the I delta omega multiplied by e to the I delta omega prime, but that doesn't click because omega and omega prime are both positive. Then you have a term which is e to the I delta omega, e to the minus I delta omega prime, that would click. Then similarly, this with minus and that with plus also would click. But the last term, which is the minus I delta omega and is the minus I delta omega prime, would not click again. So although you have 4 such phases, only 2 of them are going to work out. Once you do that, then those terms would give you a delta function, okay, by this property. This delta function can be integrated. You can get rid of one of the omegas, okay, and that would set omega prime is equal to omega. So you get actually a omega squared times 2 omega squared times other quantities, okay, and which is what we have, okay. So you get a mod a omega squared times omega squared with a factor of 2 sitting outside, okay, and then you have various other terms. First of all, there is 1 over 4 pi sitting around outside coming from this times this factor, okay, and then when you do a sine function integration, sine squared, remember now you have omega prime is set to omega, okay, so therefore you have a sine k dot r minus omega t times sine k prime dot r times minus omega t, okay, and that integration needs to be done over r as well as omega, okay. So when you do the averaging of that expression, then you can check that that the sine function would give you a factor of 1/4, okay. Mm. Right, and this c is just the factor that we had kind of written down here, okay. Fine. So what you get is that the expression for energy takes a form like this, and we define that as integral d cube r d omega times rho of omega, and all we have to do is just collect these pieces. You get 1 over 8 pi back from here, so you get c upon 8 pi times omega squared times mod of a omega squared, okay? And that is the average energy density for a monochromatic light. Why monochromatic light? Because you have taken a fixed value of omega in this particular case, because the averaging over phases actually fixes the frequencies to be same, okay. Fine, good. So now we want to kind of study how this kind of background would affect the transitions inside the atom, okay. So that the electron could be in some state, and electromagnetic wave passes through the atom, and the electron goes to a higher energy state or to a lower energy state, depending upon whether it soaks up the electromagnetic wave or it emits the electromagnetic wave induced by the external electromagnetic wave. Either one of them could happen, okay. Now, of course, we would want to do this calculation within perturbation theory, and that would work only if the intensity of the external electromagnetic radiation is small, okay, and that would mean then that the impinging energy density is a small quantity, rho of omega is small, okay. Fine. So we will try to compute the transitions in terms of average energy density of the external electromagnetic field. Good. So let's consider. Okay. So before that, like, is this okay? This is just a description of incoherent radiation, which is a kind of solution to the electromagnetic wave equation. Okay. Okay, so let's consider a single electron atom in the electromagnetic field, and we of course write down Hamiltonian in terms of the unperturbed Hamiltonian H naught, which of course includes all the things that we have done so far, namely solving the Schrodinger equation for hydrogen atom, take the fine structure corrections into account, and take hyperfine structure corrections into account. And we are saying that the external electromagnetic field is weaker than any of these corrections that we have looked at. And therefore, we treat H1 as a perturbation over this H naught. Okay, so we know what this H1 is going to look like. We have done it earlier. When you turn on an external electromagnetic field, you replace P by P minus EA by C, and then you expand that P minus EA by C whole squared by 2m, you get variety of terms. You also add a Coulomb potential to the potential part of the Schrodinger equation, and that's why you get minus E times phi, which is the Coulomb part of the term. This piece is not the Coulomb potential that we used in solving hydrogen atom problem. That is the Coulomb potential generated by nucleus. This is the Coulomb potential which is external. Okay, we are going to set that to 0, but generically, when you say that there is an external electromagnetic field, you would write down all kinds of terms. So this is one of them. The other term that you would get when you expand P minus EA by C is a term of this kind, which is E by M times A dot P. Okay, there is just another term that you would get, which is P dot A term, but P dot A term would vanish because we have chosen our gauge to be del dot A is equal to 0. Okay, so that term goes away, and in addition to this, there exists a term which is proportional to A squared, or A dot A type term, but that is the term that we are going to ignore. The reason why we are going to ignore that term is because we have assumed that rho omega or A omega is small. Okay, so if A omega is small, then A dot A term would be even smaller. Okay, is that fine? Okay, so I'm assuming that I'm still connected. So what we are going to do is, of course, choose that phi is equal to 0, which is the Coulomb gauge choice that we have made. Okay, and then substitute A, which is what we have obtained for the incoherent case, as integral d omega A omega times cos k dot r minus omega t plus delta, and the fact that we have A dot P is actually going to become epsilon hat dot P. Okay, fine. So we can just open up this cost function and we can write that as a term of this kind. I forgot to put a factor of half here because cost is exponential minus this exponential by 2 actually. So I should have put factors of 2 here. See, but yeah. So you get an expression like that. Okay, and we want to see how these terms affect transitions. Okay, fine. Okay, so what we are going to do is to basically write this Hamiltonian. I should have written H1 here really as the omega dependent pieces which we want to pull out, and write down the non-omega dependent pieces as H1 plus, okay, for the first line, and H1 minus for the second line. Okay, so that basically involves either the I k dot r kind of time term, epsilon dot p, okay, and also A omega. Okay, So we want to ask how these terms would affect the unperturbed energy levels. Okay. Now, the reason why we want to pull out this expression and write it in this particular form is to explicitly show that H1 plus and H1 minus are the terms uh, which uh, which involve expressions like a omega e to the I k dot r or minus I k dot r times epsilon dot p. These are all pieces which are time independent, but the total Hamiltonian is actually time dependent because you have e to the I omega t or e to the minus I omega t sitting around. Okay, and the reason why we have pulled e to the I delta omega out is because delta omega also has a weak time dependence, much weaker than e to the I omega t, but nevertheless it is there. Okay. So in other words, if you want to study this problem in perturbation theory, what we need to do is to use time-dependent perturbation theory. Okay. So let's try to kind of quickly recap the time-dependent perturbation theory. But before that, any questions? Okay. So probably there are no questions. So suppose we have the eigenfunctions uk of r, okay, which are the eigenfunctions of the unperturbed Hamiltonian, which is the H naught that we have written down here, which is of course more complicated stuff, but we don't really care. If you know that there exists some eigenfunctions of that Hamiltonian corresponding to that there exists some eigenvalue Ek, then we start our problem by defining our time dependent wave function to be uk of r at time t equals 0. Okay. Now, at time t equals 0, we have not turned on this perturbation. Okay. So, so that is how we start with the unperturbed problem. Okay. And then we turn on the perturbation H1. Okay. Fine. Now, once we turn on the potential H1 or the perturbation H1, okay, we keep that perturbation on for some time, less, and we call that time to be capital T. So for that much time, the perturbation is on, and then you switch it off again. Okay. And what we want to do is we want to compute the probability of finding a particle in some other state, uh, say uh, uh, say some u of p at r. Okay. So we of course want to normalize that by saying that, like, what is the probability of finding that per unit time of turning on a perturbation. Okay. Good. Now, what we are doing really here is that um, we want to write down this wave function at time t equals 0 as some arbitrary linear combination of the wave functions. Okay. And that is how we normally do it, time dependent perturbation theory. But if you want to say that you want to start with one specific wave function, then all that one is trying to say is that at time t equals 0, this ck is non-zero only for a particular value of k. Okay. For all other values of k, the ck would be 0 at time t equals 0. Okay. The ck may have different non-zero values at all times after that. Okay. But at time t equals 0, you just said that to be equal to a specific value. Okay. Fine. So here's the thing that we write down the wave function like this, and we want to ask how the how these parameters Ck of t evolve as you turn on the time dependent perturbation of this kind. Okay. Now, of course, to do that, you will have to solve the time dependent Schrodinger equation. But time dependent Schrodinger equation is written in terms of a quantity like this. Okay. That means you substitute wave function to be something like that. Okay. In this wave function, the original wave function that we have written down, which is uk of r, is time independent. Okay. So therefore, evolution of the wave function with respect to time, which is done by I del del t of acting on psi, would actually give you a factor involving time derivative of Ck of t. Okay. Now what we want to do is that we want to ask what is the overlap of the initial wave function with the final wave function, which involves Cb of t. Okay. So uh, so what we would do is that when I del del t acts on this one, uk just passes through because there's no time dependence. When it acts on e to the minus ikt, it gives you a time independent Schrodinger equation involving uk. But when it actually acts on c, then you get an expression which is like this. Okay. Right. So time evolution of these coefficients is given by the matrix element of the perturbation Hamiltonian between the initial state and the desired final state B. Okay. And clearly the amplitude will depend on omega B minus omega K. Okay. Okay. Okay, so now what we are going to do is we are going to solve this equation iteratively, means order by order in perturbations. Okay, so to do that, we first realize that this amplitude, okay, you are looking for transition. Okay, so clearly the state K written here and the state B written here are not same. Okay, so if those states are hello, hello,
Yeah, so you cut
yeah,
off for a moment.
yeah, no, actually. I got a call from the doctor about my father's appointment. That's why I had to kind of terminate the thing for the time being. Okay, let's get back to what we were talking about. That we want to solve this uh, equation order by order in perturbation, and we are looking for transitions. That means K and B are different, and therefore this matrix element is already first order in perturbation. Okay, and therefore uh, the Ck that we get on the right hand side should be just treated as a zeroth order term. Okay, so the leading term. Otherwise, like the CB, CK also would be evolving in the time dependent perturbation theory. So what we will do is that we will just assume that this state is a fixed state, and that we know, we have defined that to be delta K A. Okay, so we substitute that at time t equals 0 and compute CB dot by computing this matrix element, setting Ck to be just delta Ka. Okay, and we have either minus I omega b minus omega a because of this delta function times t. Okay, so that is what would be the expression that we would get. Okay, this entire sum would go away simply because although we have written down this to be a sum, at time t equals 0, only one of the terms is going to contribute. Okay, good. So now we know what H1 is. H1 is written up here. It contains two time dependent pieces and H1 plus and H1 minus. We just put that in. Okay, and we have e to the minus I omega t, e to the I delta omega times the matrix element of H plus between really H1 plus, but yeah, between A and B, and matrix element of H1 minus between A and B with e to the plus I omega t and minus I delta omega. Okay. Now, and we are going to integrate over d omega. Okay. Fine. Now, left hand side involves CB dot. Okay, and we have to kind of solve for CB, so we have to kind of integrate this quantity, but this integration would require one boundary condition, but that is kind of something we know trivially, and that is at time t equals 0, CB was 0. And the reason why it was 0 was because we want to look for transition, and therefore B is not same as A, and therefore CB 0 should vanish. Okay. Good. So if you look at the behavior of CB at time t, then it basically is just the value of CB at time capital T and no contribution coming from anything in between to first order in perturbation theory. Okay. Good. So okay. So what we are doing here is basically carrying out the integral on left hand side with respect to time and an integral on the right hand side with respect to time. Now, when you do integral on the RHS with respect to time, then you notice that you get terms of two types. You get e to the I omega BA minus omega times t, or you get e to the I omega BA plus omega times t. Okay, these are the two factors that you would get. Okay, and if you do that integral, then you time integral, then you get this factors omega BA minus omega or omega BA plus omega in the denominator, and this term in the numerator. This term you get simply because of the endpoint contribution of the integral. The integral is done from time t equals 0 to capital T. Time t equals 0 is this contribution, capital T is that contribution. The other term has the other way around expression, okay, which is omega BA plus omega. Okay, so that is what CBT would be. CBT, this expression should have been CBT minus CB0, but as we just argued, that CB0 just vanishes. Okay, so it's explained here. What we have done is we have used this integral 0 to t, and you get this answer, which is what has been substituted up there. Okay, fine. Now, of course, we are doing incoherent, looking at incoherent radiation. So therefore, we should be summing over all delta omegas. Okay, so that we would get the kind of incoherent sum over all the phases. Okay, so that is why this sum over delta omega is inserted here. Okay, so this is of course the amplitude of finding the particle in the state B when you started with the initial state A, which is different from B at time t equals 0. Okay, so this is the behavior. So let's compute the probability. So for that, you will have to compute mod CB squared. Okay, due to incoherent sum, of course, we have the result that e to the I delta omega, e to the I delta omega prime would just average to 0, and e to the I delta omega, e to the minus I delta omega prime would give you a delta function. Okay, something we discussed a couple of pages ago. Okay, so when you take a mod square of this quantity, then you will see that if you take a mod square of this quantity and a mod square of this quantity, you would have contributions. But if you take cross terms, you wouldn't have any contributions between them. Okay, because complex conjugate of this, we would have e to the minus I delta omega multiplying with this function, will also have e to the minus I delta omega, and vice versa. Okay, so that is why incoherent sum would have mod square of this and a mod square of that. Okay, and no cross terms. Okay. Okay, so this is something I had mentioned some time ago, that we would get two integrals because you are doing mod squares of these quantities, but one of the integral can be eliminated by using the delta function. Okay, so that is the averaging process, which gives you a delta function. You have a single integral over omega left over after eliminating that delta function through one of the integrals, and what you get, as I explained a few minutes ago, is mod square of h plus and a mod square of h minus, and no cross term. Okay, so that is the reason why we call it incoherent. Had it been coherent, you would have also got a cross term of b h plus a star multiplying b h minus a and vice and complex conjugate of that. Okay, we don't have that piece. Okay, good. So all you have to do is to kind of look at this expression, okay, and take mod squares, and you can write down this quantity by pulling out e to the I omega b minus omega t by 2 outside, and then you get this quantity minus e to the minus I quantity, which can be written as sine function. Okay, and the e to the I omega b ba minus omega t by 2 factor sitting outside would go away, because when you take mod squared, those factors would drop out. So you get a function which is sine squared simply because this itself gives you sine, and mod square will give you sine squared. But the argument, which is omega ba minus omega t by 2, okay, that is the important thing, that you have a factor of 2 sitting around here. The factor of 4 comes simply because e minus e kind of factor is 2 times sine, that's why 4, and then the denominator squared is sitting around here. Okay, so once you get this factor right, the other factor is basically the same. It's just that omega changes sign. Okay, so that is what you get. Okay, good. So the time dependent part has been taken care of right now. There is a piece which is something that we need to compute, is the one which is time independent. Okay, and h plus h minus are just the same expression, except the right moving versus left moving wave. Okay, fine. Good. So when you want to substitute this inside these matrix elements, we can pull out certain terms like e by 2m and a of omega, and all are just going to pop out of these matrix elements because they have no role to play. And only quantities that we are interested in are the quantities written out here. Okay. Fine. So, so let's kind of go back and look at the way the rho was defined, which was the energy of the electromagnetic radiation, which was omega squared mod a omega squared with c by 8 pi. You will see many of those factors kind of coming out of inside this expression. You have a factor which is c is sitting around here, and A omega is sitting inside this, which is, of course, when you pull out of this mod square, you'll get mod A omega squared factor. Okay, so you can write down that entire expression in terms of rho. Okay, so barring the matrix element of H plus involving e to the I k dot r epsilon dot p, everything else could be written in terms of the energy of the external electromagnetic radiation, namely the rho. Okay, fine. So one can kind of write down CBT mod square in terms of rho. Okay. What we want to actually look at is the transition rate. So we would divide this whole mod CBT squared by the time over which the perturbation was turned on. Okay. Good. So if you do that, then if the time is large enough, then the contribution for the transition comes from the terms where uh, omega BA minus omega kind of vanishes. Okay, so that is basically you're just pulling out the contribution when the denominator is small. Okay, so that is the main contribution. Okay, so okay, now if you look at the other expressions, so even if the denominator becomes small, the quantities, the remaining quantities that we have are all finite. This is a sine function, so it takes finite values. Okay, bounded between 1 and -1. Okay, and this matrix element is, I mean, we are already treating this to be a small perturbation. So this matrix element is a quantity which involves the oscillatory function and epsilon dot p, and for kind of for any of these states, epsilon dot p would be a finite answer. So all other quantities are finite. Okay, so there are kind of bounded values for all these quantities, the matrix element as well as the sine function. Okay, fine. So in that case, for large t, what we could do is we can just replace omega BA by omega. Okay, so it's like saying that that is the dominant contribution. Okay, right. Now, omega BA is just the energy difference between the two states between which the transition is happening. Okay, uh, and if you look at omega BA to be positive, okay, so let's go back to this expression again. Okay, so if you take omega BA to be positive, then only term that would contribute is this. Okay, because this is positive and this omega is positive. Okay, this omega is positive because we are working in the real basis for the electromagnetic radiation, and omega was positive semi-definite. Okay, so if omega BA is positive, that means energy of the state B is larger than the energy of state A, then we would have a contribution coming from here. If omega BA is negative, then this is the one which will contribute. Okay, so that is what we are talking about. Okay, so let's choose one of the two things. So what we are looking at is the transition from the lower energy state to higher energy state. So omega BA is positive, and in that case only the first matrix element is going to contribute, and so 1 over T times mod CBT squared would be, I could have written the whole thing in terms of rho, but nevertheless is C times E squared upon 4m squared, which is the factor which comes from the perturbation Hamiltonian. Mod square will give E squared upon 4m squared times mod A omega squared, it's all factored out, times mod square of the matrix element M plus just represents these pieces, e to the I k plus I k dot r times epsilon dot p. Okay, the matrix element of that at omega is equal to omega BA times 4 times integral d omega of sine squared this argument upon omega ba by omega minus omega squared by t. This t is simply because we are dividing the whole thing by t. Okay. Fine. So this m plus minus is the same thing that I just mentioned. Okay. Okay, so let's kind of do this integral and stop. It's already 12:30 actually. So to do this integral, we make some change of variable. We just replace omega ba minus omega by 2 times t to be x, and write this integral as dx times 2 by t times sine squared x upon this quantity is 2x by t whole squared times t. Okay, so you can kind of manipulate this quantity. You can see that this comes out to be half because of this factor of 2 sitting around times sine squared x upon x squared. Okay, and this integral is known. You can compute that to be pi by 2. Okay, so we know how to compute this particular integral by using the change of variables. Okay, so what you get is the factor pi by 2 from this. There is a factor of 4 sitting outside. So take them together, you get the answer 2 pi. Okay, so what you get is a quantity which is CBT mod square upon T is equal to E squared upon 4m squared, C mod A squared. These are all factors which are sitting around in the previous expression already. Okay, then there is a matrix element mod square evaluated at omega is equal to omega BA. That means the energy is sufficient to effect this transition from state with energy EA to the state with energy EB times 2 pi. Okay, so you can kind of put that back in and write down this expression in this particular form. Okay, so what we will do is that we will kind of substitute this expression in terms of rho and try to compute this matrix element in a particular approximation, but let's do that in the next class. Okay, so what we are going to do is basically use what is called the dipolar approximation, which we can look at later. Okay, so I have not put these notes in the Dropbox yet, but I'll do it soon. Okay, so I'll stop here. Any questions?